All right, let's take a look at this problem. We're going to use integration, of course, here to find the volume of a pyramid that has a height of 15 feet. And the pyramid has a square base of side length 10 feet. Okay, so we've got a square base. I'm not going to draw the three-dimensional picture here, but if you were looking from the side of the pyramid, of course, we see a triangle. But this base down here is square. Okay, its side length is 10 feet. All right, and so I'm going to set this up. I'm going to integrate with the pyramid lying on the x-axis, if you will, at y equals 0. The height of it is 15 feet, so this horizontal line is y equal 15. And again, what we need to do is we need to find the area of an arbitrary cross section. So I go up to an arbitrary height. We call that y. Y is going to vary, of course, from 0 to 15. But at that height of y, what I want to do is just cut right through here and slide that piece out and look at it from above. If I'm looking at it from above, what's it look like? If I'm looking at it from above, it's a square, right? Because the base is square, so these squares are getting smaller and smaller as we get to the top of this pyramid. Okay, and so we have a square cross section. I'm going to call this distance here A. This distance here is the side length of this square cross section. Notice as the pyramid gets bigger, these square cross sections are getting smaller and smaller, right? Approaching 0. My goal is to get an expression for the area of this square in terms of y. As y gets bigger, what's happening to the area? Well, obviously, if the side length is a, we know the area is just a squared. Okay, so how do I get a, little a, that is, as a function of y? Well, I'm going to use similar triangles. You can see I have the big triangle itself, which is a cutout of the pyramid. The base is 10 and the height is 15, right? Going all the way from y equals 0 to y equals 15. Well, this triangle here, let me sort of outline it, is similar to that bigger triangle, right? It has the same angles. They share this same angle, and these angles are the same here and here, and these angles here are the same as well. And so this is a scale down version, if you will, of the bigger triangle. And so we know this small triangle is in proportion to the bigger one. Therefore, their side lengths are in proportion. What's that mean? Well, if I take the small triangle here, its base is A, and what is its height? Well, remember, this is Y up to this point, which is the bottom of where that rectangle is. This is the height of the I keep saying rectangle, sorry, triangle, height of this triangle, right? And so what is that? Well, if the total height is 15, right, from y equals 0 to y equals 15, and this is y, then what's left is 15 minus y. So that's the height of this small triangle. So if I take the ratio of the base of that small triangle A to its height, 15 minus y, that would be the same as the ratio of the big triangle's base, 10, to its height, which is 15. So this equation here is where we're going to get the value, get A expressed in terms of y. Now 10/15 is 2/3. And if I multiply both sides, so I've got this, right? A over 15 minus y equals 2/3. If I multiply both sides by 15 minus y, I get A is 2/3 times 15 minus y. So there it is. If I square this, square 2/3 gives me 4/9. Square 15 minus y, I get 15 minus y squared. And so since the area of this square is A squared, here is the important area formula that I need. Okay. So that's the goal, is to get the cross-section area. And this cross-sectional area could be could be a square as is here. It can be a circle, right? It could be a rectangle. It could be a triangle. There's many shapes. Whatever that is, you can get this length here, right, as a function of y, as we did here, and then you would be able to get the area of the cross-section as a function of y. And notice this area makes sense because, as we said, the area at the bottom is what? It's a square with a side length of 10, right? So 10 squared is 100, right? So the area when y is 0 should be 100. Is that true? If I plug in 0 for y, do we get 100? Well, I get 15 squared times 4/9, and if you do that calculation, that is going to be 100. Okay, so when y is equal to 0, this is 100. And notice that area, those cross-sectional areas, as y gets bigger, the value of a is getting smaller and smaller. The squares are getting smaller and smaller. By the time we get to y equal 15, the area has gone to 0. And notice if I plug in 15 for y, I get 0 here as well. Okay, so that's important to confirm that. But now, so far, what calculus have we done? None. So how do we find the volume of this pyramid? We are going to integrate, right, the cross-sectional area from y equals 0 to y equal 15. So let's do that. So I just take that cross-sectional area here. Here it is. Here's the area of the cross-section as a function of y. And I'm going to integrate from 0 to 15. You could expand 15 minus y out, right? Square it, and then just find the antiderivative that way. I'm just going to do a little substitution. I'm going to let u be 15 minus y. du is negative dy, and so negative du is dy. I'm also going to change the limits because I'm changing the variable. So if x is 0, I said x, I'm sorry, y. If y is 0, right, then u is what? 15 minus 0 is 15. And if y is 15, the upper limit, 15 minus 15, u is 0. So after we do the substitution, we're now looking at the integral going now from 15 to 0, right, because of the new u limits. And then the dy is negative. I pulled that negative out. Du, this 4/9 I pulled out as well, so I get negative 4/9, and then I'm left with 15 minus y squared, but u is 15 minus y, so I get u squared. So now I'm just taking the antiderivative of u squared, and it's pretty easy to do. Now, you could just integrate as is here. If you don't like having the lower limit bigger than the upper limit, that's okay. You can swap the limits. Remember what has to happen, though. You change the sign out here. So from negative to positive, this is now going from 0 to 15. You can integrate either way. Doesn't really matter. You'll get the same result. So what is that result actually? Well, if we find the antiderivative of u squared, as we said, that's 1/3 u cubed. And so plugging in 15, plugging in 0 and subtracting, we get this expression, which is equal to 500. So the volume is 500 cubic feet. So the integration is not that bad. It's just setting it up so that we get this volume. Okay. All right. So I hope this is helpful for this volume problem. They are sometimes challenging. You want to certainly draw the picture, and the key is to get that cross-sectional area as a function of y if you're integrating with respect to y as we're doing here. Okay, hope this is good.